some work which I've been doing recently. And it's a great honor and privilege to be in this meeting, which is celebrating Sriram's achievements and the 66th birthday. So, I think, as you all know, Sriram has a great influence in Indian science. And, I wanted to say this thing because we are organizing a meeting in December on soft matter, which is an annual meeting of the soft matter community here in India. And this is the 17th edition of that. And all the abstracts we received, the maximum number of abstracts are in active matter. Okay? And so much so that we have to increase the number of sessions in active matter in India. So that is, so this is the, I think great influence. I think it came from this I think from Sriram basically, and others. What I wanted to talk to you about is the collective motion of self-propelled ring polymers on circularly patterned substrates. This is a work which is done with an extremely bright undergraduate student, master student, Haoshang Wen, and Mohammed Laraji, who is at the University of Memphis. Haoshang is now a PhD student at the University of Chicago. So this work, as when you talk about self-propelled particle collective motion, there's a huge amount of literature. Okay, so and I'm not going to even attempt to cover any of that here. Okay, but just as an introduction, I would wanted to just show you a few of the things which are very important. For example, a variety of geometric shapes, interactions, and driving mechanism have been studied. Right, there is a lot kind of shapes, and these systems are, as somebody said, it catches your imagination. It's your imagination what kind of particles you should put in, and you get something non-trivial. Okay, so this is that way an exciting system. So of course, starting with the initial one was the one which we all know is the Wicksec model, in which we have point particles, right? And then that is in 1995. And your point particles, which, if you increase the density, it'll clump and form these clusters. And if you add some noise and increase the density further, but add more noise, it will become again, randomized. But then reduce the noise, it becomes again aligned, right? So this is maybe the one which started off this area in some sense. And then there is again more papers. And this is a paper which comes from the Sackler group, and some authors are here in the audience. And so this which shows again that if you have point particles with nematic coupling, again you can get a very rich phase diagram from that. Okay. And there are other models which looks at disks with polar fields, which which are now, when they clump, they reduce they inhibit when they contact inhibited locomotion. Okay, and that has been studied in detail in this paper. So that's another model of this type. Okay, and there are models which look at other shapes than point particles. So point particles to disks. I'm just showing some examples from each of them. Point particles to disks, and then to rods and shapes. Okay, and then here we have this Prerna et al. So they have done very detailed work, many papers, and this is showing that the particle shape, the anisotropy of the particle shape, can lead to clustering, and this is this way, and this is this way showing that in increasing activity or increasing polar order can also increase clustering, and that is this one. And then, of course, there have been composite particle models. Okay, and composite, and this work, because I refer to this especially because there is some similarity between what they observe and what we observe in our models. And then there's the composite particle models of cell motility for them, which has and two particles, which introduces a shape in the front between the shape change between the front and the back. Okay, that's another type of model. Okay, so I will not go into any of those details right now. Okay, so I wanted to show, and there's a whole sort of other class of models. Okay, which is now used to model collection of cells. Okay, so now there is these models are popularly known as vertex models. Okay, and maybe the first one I could see is this reference, but maybe there are other references, and Max B et al. Done a lot of work on this, and so that is the network connection model or the vertex models. And then there is phase field models, which is Julia Yeomans and other people, and they have the phase field models, which also for which each particle is a field. Okay, so there's as many fields as many particles are there. So, and these models are mainly for collection of cells to understand that with the, and the point is that all these models assume confluence to be close to 1. So everything is touching each other, okay, and so that is one important restriction in this model, okay. And so what we wanted to look at was actually, or this one is, that we are looking at a simple model for a ring polymer model for a cell, which can represent a deformable cell in varying dimensions, varying densities. So I say can because we have some more work to do. We have not reached there yet. Okay, but what I will show you is the model and some preliminary studies on that in this ring polymer model. And to make it into represent a cell in a tissue, it needs some more work. Okay, so this is the model. So we mark the boundary of a cell, or the projection of a boundary of a cell onto a substrate by a ring polymer. Okay, and then this is what it is, and the ring polymer has n beads, okay, which is connecting a ring polymer. And most of the work and result I'm going to show you here for n is 40. Okay, and then we have a semi-flexibility on the thing. Okay, and we have a polar. We mark 2 points and then define a polar vector. Okay, that's called PL here. L is the index for the ring, and P is the direction of the polarization, okay, which we have. Okay, and this is the net energy of that system. Okay, which has a bond energy, which has a bond potential. Okay, which is connecting the springs, connecting the thing. Okay, and you have a bending energy, and so you have a repulsive interaction between the rings. Between these things to connect to make the rings not overlap each other, okay, and then you have a bending potential, which is to keep it semi-flexible, okay, and then we have an area constraint, okay, a compressibility term for the area, and this is also important because we have not seen works which introduce this one, okay, and these are the papers in which this model has actually appeared, okay, and so now to add propulsion, okay, what we do is to add a force term like this. Okay, this is the polarization direction, and you have a force term, okay, which is given by this. FD is the strength of the propulsion. Okay, and as I said, is the number of beads in the thing. Okay, and P is the direction of this polarization. Okay, and so this is just to say that this is a unit vector in that direction, and then there is a term G. Okay. The GBPI, and which has this property that it takes plus or minus 1 depending upon A dot B is greater than 0 or less than 0, which basically introduces switching of the direction. Okay. And where V here is a velocity integrated over a time tau. Okay. So it kind of gives a persistence for the velocity before it switches. Okay, and that is this is the model, and this kind of term is similar to what you can see in this particular reference. Okay, again, in the context of cell motion. So this is what the model is. Now the model has the elastic terms, and then there is this propulsion term. Okay, this defines the model. And this force acts on every monomer ion. And this is going back, right? Yeah. Okay, so the preferred angle, so we also do one more thing. We have a preferred, the angle normally is for the thing, there is a preferred angle at these 2 points, the thing, and that is tuned to make this change the shape of the cell. Okay, this could be circular. If I keep it 180, then it's almost circular. Okay, and if we can change that preferred angle, then it becomes, again, it can be elongated shapes. Okay, so that is the way we change the shape of the cell. Okay, so that is what, and now the beads move according to the molecular dynamics scheme once you define that in U-shape. So that is that's what we have in the model. Okay, so this model is now well defined, and then we go into. I just show you now some some results from the model. Okay. So now this is as a function of this is a high densities, and packing fraction here basically means the number of beads per the area of each bead to the total area, and that's a packing fraction is. Okay, and this packing fraction is fixed at 0.3125 here. Okay, and this is 4 digits because we just fix the number of beads and then we get this packing fraction. Okay. And the angle of as I said, the two angles are kept at 120 degrees at the two poles. Okay, so that the cells are elongated, as you can see. Okay. And you see that as we increase the driving, okay, or decrease the driving, the cells, the clustering disappears. Okay, or increase the driving, you start getting clustering. Okay, and this is with periodic boundary conditions. And what is shown here is the velocities of the instantaneous velocities of every particle, and you can again see that this cluster has a correlated velocities. Okay, and there is I hope you can see this. This is a bit small, but yeah, you can. This cluster shows correlated velocities, and then otherwise it's randomized. Okay. So increasing amplitude of motility forces leads to clustering of elongated cells. Is what we see here. Okay, so this is. Said this kind of clustering has been observed in various other contexts, but this whole cluster moves as whole thing. It is not jammed or something in this densities. Okay. So now one of the points which I wanted to show you was to say that okay, now this is how it moves. Okay, the cluster. Okay, and if you want to show that the shape is important, because if I make it into a circular one, okay, and then what I see is that they don't cluster as much. Okay, that's again demonstrated here. In this snapshots here, we can see that this even if we increasing driving force, we don't see clustering of the spherical cells. But if in elongated cells, they move in a direction. We can also quantify it more to show that they really don't have a long-lived cluster. Okay, but anyway, that's not shown here. Okay, and so we can. On the contrast, I wanted to show you that in the case of elongated cells, you actually see clusters and you see a correlated motion of them and the velocity field also. Okay, so now so that is so the clusters are highly dynamic and the circular rings do not exhibit collective motion. So the shape is very, very important in this particular case. Okay, so now we can go into asking. We can quantify this more. We can calculate this Weikstraff order parameter, which is the velocity correlation, and we can look at how that changes with the driving force. Okay, and this is for the blue curve is for the elongated cells. Okay, at densities 0.3125, and and this is for a lower density for elongated cells, the red one, and the green one is for circular cells, and you can very clearly see that there is a transition at a density at a particular driving force, and if I look at the fluctuation in this order parameter, you do see a peak. Okay, showing that it is a continuous transition there. Okay, we can, on the other hand, we can look at the polar vector orientation. Okay, the same order parameter with polar vector instead of the velocity fields. Okay, this is with the velocity fields and this is with the polar vector. Okay, defined, and you do not see that kind of a strong increase in the polar order. Okay, so what we see here is that the pneumatic order parameter with the polar directions, okay, doesn't show very strange, very strong change. Okay, but you have, which they are not as strongly ordered in the polar direction as that in the velocity directions. These particles are, and they form the clusters. Okay, which about to summarize, which says there's a cluster formation, and the clusters have velocities correlated in that. Okay, and but their polarities are not as strongly ordered as the velocities are. Okay, so that is what. So what is the mechanism for that, and what is the reason for these two things? That one is shape is important, and also that these velocities are not correlated. Sorry, the polarities are not correlated. We look to just understand that we look at two particles. We just focus on two particles colliding in the simulation. Okay, and we keep track of that, and we see that when this is two particles coming in, and green is the velocity direction, and the black one line here is the polarity direction. Okay, and what you see here is that as they come and they collide, okay, and they collide, and then their velocities align, okay, but their polarities don't align. Okay, the polar directions don't align. Okay, and if you remember, the force is acting in that direction, and then this is the green region here is a region where they stick together. Okay, and then they align there is a time where the velocities are aligned, but the polarities are not aligned. Okay, and when the polarities also align, they start separating and going away. Okay, they go away. So they stick together by just basically bumping against each other and deforming the thing. So if the particle is very rigid, okay, and for example, in the case of like in a circular shape, okay, and they don't stick, so they just go away, and that's what even here we are trying to show. Okay, so so to summarize this part, I just wanted to say that okay, the misaligned polarities keep the cells pushing against each other, and deformability is important. So now you can ask the question that what happens if it's elongated and rigid? We have not been able to do that simulation because our model doesn't really go into that. Okay, so that part is still left out. But in the case of circular thing, we can see that it doesn't.
Sunil, sorry, just quick. So when you say circular, you just mean so stiff that it can't deform. Is that basically what you're saying? Or?
Yeah, it's both. Yeah, it is circular in shape and it is stiff. Right.
Oh, so there's a mean shape and there's a deformability.
Right.
You're saying
we are looking at two regimes where it's elongated and flexible, and it is circular and rigid.
That is elongated means in a permanent sense, the mean shape itself is given to be elongated. Okay, thanks.
By fixing the two angles at the
okay.
Yeah. Okay, so now we're going to the part where we look at the same cells. Now we confine them in a circular boundary, okay, with a circular boundary in 2D, and we have an inner region which is patterned, okay, like we heard yesterday, okay, or from Sanusan's talk, that there's a patterned region, okay, where it is allowed to move in a circular fashion. Okay, so there are these tracks, okay, which are patterned, and that patterning we impose on the particle by putting in a potential of this form, okay, which is basically aligning any particle, okay, in the tangential direction, okay, and that is what this is doing. Right? Okay, so now you can get that through grooved substrate. We saw that in the talk on the first day. Okay, so now. So again, the potential is now the same, but except that now we have added this extra substrate potential. So, and that whenever I say Ks, that is the strength of that substrate potential which I will be using. Okay? And then the equation of motion is the same. Okay, and so this is the details are here in this paper. Okay, so now we look at the few movies of that. This is low densities. Okay, low densities, and now there is a substrate here, and this is the substrate potential is 0, means there is no grooves here, okay, and then they just move right around, okay, they collect to the boundary, okay, and then as I increase the density, they have more particles collecting at the boundary, which as Sriram showed, that is a very generic phenomenon of all of this thing. When you confine them, they go to the boundary and they get stuck there, and then they have this rotational motion of the particles. And so this has been seen in many things, so it's nothing new there. And now this is a case where there's a substrate potential. Okay, now there is an inner substrate, okay, where it is now confined. Okay, the inner region where it is there is a circular patterning. Okay, and the pattern potential actually keeps the particles there. Okay, and what we see is that at these densities, particles actually go there at these driving forces. Particles go there and get accumulated at the boundary between this pattern and non-pattern region. Okay. And this boundary can actually, and then they rotate, and they can rotate either in the same direction or in opposite directions. Okay. So in the boundary, the particles accumulate, and then they can then rotate either this direction, the same direction, or in the opposite direction at this particular densities. Okay. So this is one regime which you see this. Okay, and there is exchange of particles between between these two regions. Okay. But what actually happens is that there is more radial flow outside than inside, so that particle gets collected there. Okay, so we try to understand this a little bit, and so we look at this. Basically, I'm summarizing the movie here. Okay, you have this patterning region. Okay, and so when the substrate potential is 0, then you don't have any accumulation of particles here, only at the boundary. When the substrate potential is there, you have accumulation of particles there, and then they can move in either same direction or opposite direction. But as you increase the force, okay, this region is more and more depleted, and then the particles all go into the boundary. Right? Okay, now that that depletion, that this thing we can quantify, we can look at that, and then we can show that if there's a periodic boundary, okay, and so where there is no substrate potential, then the density is uniform, okay, and if there is a substrate potential and then there is a peak at the boundary, and this basically comes from this fact, as I said, that there is less particles going out than coming in, and because here the particles tend to move tangential direction, and while outside particles are moving in all directions. Okay, so we can also quantify this by just computing another order parameter. Okay, sorry, I use the same symbol for the Vixich order parameter, but this is not a Vixich order parameter. This is basically looking at all particles, which direction it is moving, which clockwise or anti-clockwise, summing over all particles, okay, and taking the mod of that and then doing the average. Okay, and that is what this order parameter is. Okay, I can look at that, and I can look at that as a function of the driving force, and you will see that this as you increase the driving force, there is a transition. Okay, and there is this region of the driving force in which this could have dual rotation. Okay, and hence there could be a decrease in this order parameter. Okay, so I think I'm almost done with my time. So just to show you one more thing. So what is the reason for this? This is just showing you that why the particles accumulate. Basically, as I said, the particles accumulate because each particle in the pattern region actually do a spiral motion, because there is forward propulsion and there is an aligning force. So they do a spiral motion and they go to the boundary. Okay, but at the boundary they get so they have more, and then they escape from the boundary. So that is one way, and then the other particles come in from outside. Okay, so and that is the reason why you have the accumulation of particles at the boundary. And since I don't have time, I will not spend too much more time on this. And I just want to now show you the effect of the packing fraction. Okay, and that is, I want to spend a few minutes on this. Why this not? Huh? Okay. It came? No. Yeah, okay, now it came, yeah. So, yeah, so you can see that the packing fraction, that's how it moves. And now this is much higher packing fraction, so we're going to 0.6, okay. And this is again, this pattern region in the middle, okay. The pattern region has, that is Ks not equal to 0. And you see there is a depletion of particles from the pattern region, okay. Everything goes into the boundary now, okay, at high densities, okay. And if you have very high densities, about around 0.8, and then they exhibit this, reversal of the rotation. Okay, so they all rotate coherently. Okay, and at some point they reverse the direction. Okay. And you can see that actually that reversal originates from the center. Okay, and then the whole thing goes around. And yeah. So this is, then again, we can look at this in detail, and we can see that, if you look at for different substrate potentials, okay, so it depends on the substrate potential, and if it is 0, okay, substrate is 0, then the velocity is one sign, okay, doesn't change the sign, okay, but if you increase the substrate potential, they undergo this change in the direction, okay, and we can look at we have not done too much analysis on this, but we can look at we can take a long time series and then look at the Fourier transform of that, and we do see a peak, indicating that there is some kind of a quasi-periodicity in this rotation. But we don't really understand what causes that reversal, okay, except that it's some, at the center where it has to be high densities where this depletion. See, if you have low densities, you have this depletion zone here. Okay, particles get depleted from the center. Exactly at the density at which this depletion zone vanishes, so that is, particles are forced to be in the depletion zone, is where you start seeing these reversals. Okay, so it's basically originating from the center of the thing. So I think that is what what I wanted to say, and just wanted to quantify that again here. Okay, we can look at it as a function of various densities. Okay, and where this density, the depletion zone vanishes. Okay, so this is rho itself. Okay, and where this depletion zone vanishes. Okay, and that's the point at which you see this reversal of the vortex motion. Okay, the direction of the rotational motion. So that's all I wanted to say, and this is a conclusion of the thing. If there are any questions, I can take them. Yeah, thank you.
So why does the reversal happen from the center? If you have a reversal motion, like reversing motion happening at the boundary, will it persist or will it not persist?
No, it doesn't happen at the boundary, and it doesn't propagate inwards. It always propagates outwards.
So do you have an understanding as to why that does?
Not very much, except if they see that it is because the particles in the center, when particles get into the center, because there is also a circulation of particles. Particles slowly go in and then get out. So when the particles come to the center and then get into this groove, as they try to move out and they get into the groove, they can go in either direction. Right? So I think what we observe is that when 2 or 3 particles get in the wrong direction, and then it's able to force the whole thing to move in the opposite direction. I don't really have a full understanding of this. It's just what we observe. Yeah.
Can we come back to?
It's just the force in the direction.
In the beginning, your FP, the slide where you define your FP. So L1 and L2 are fixed. You impose L1 and L2. How do you choose them? I didn't get that. Yes, they are fixed. And then, is this a force or is it a force dipole that you should have?
Oh, this is just a force, not a force dipole.
But then the total internal force doesn't vanish, no?
Sorry?
This is an internal force and the total internal force doesn't
No, this
vanish.
is just a force. This is a force system. This is a system in which there is particles have a as force. It's not total force is not 0. That's true. Yeah. Yeah.
I had something similar. I was also wondering if the total force vanishes. But as a separate question, if you don't have the patterning, do you see accumulation of the particles, or do you need the patterning to get the accumulation?
Sorry?
If you don't have the patterning of the substrate, do you see accumulation of the particles?
No.
No. And once
you don't have patterning on the substrate, things accumulate at the boundary,
Sure.
but not in the.
And once you get the accumulation due to the patterning, do you need the deformability to see the rotation?
Yes.
So if I had rigid particles, they would not rotate.
So I also had a question about the active force. How do you control the persistence time? Is there any way within the model?
So that's what I'm saying. So this velocity here, this factor here, okay, is dependent on the velocity history, okay, of the particle. Yeah. So it's averaged over a certain time tau m. We can change the tau m if you want to change the.
That represents the persistence time.
No, so I'm just trying to figure out I'm trying to understand the motivation for this form of the force. I know you described it at the beginning and things, but you're saying that you have a force that cares about how the polarization on a given monomer, PL is assigned to a ring, I see.
Yeah.
I see. I guess I'm trying to, this factor G of VL comma PL, so that you look at the polarization of the ring and you look at the velocity of the ring.
Velocity of the ring, right, yeah.
And I see. You push it, okay, so can you just, I'm not understanding the motivation for this form of G of VP. There must be some simple way of seeing it.
We just wanted to control the persistence of that. That is basically the reason why we put in the thing. And we saw this, in this reference, it's been post cell motion modeling, this has been included. So we use the same form.
I see. Okay. Maybe I have to internalize a little bit more. Okay, thanks.
Okay, if not, let's thank Sunil very much.